So everybody is in. Good morning, everyone. Welcome to a hard BD and active workshop. So, I'm Shimin Chen. I'm actually in Beijing, China. I'm from Institute of Computing Technology, Chinese Academy of Sciences. So today we have a very exciting program. After this message, we'll have the first keynote, and then we have a joint invited talk with SMDB. So this year, we're going to try something new with SMDB. We invited 2 keynote speech and 1 invited talk. And because both of the workshops are database systems oriented, we would like both audience to enjoy the talks. I actually can hear my own voice. There's some, yeah. Then we will have a research session with 3 interesting papers from 10:30 to 11:30. Then after a short break, we will switch to the SMDB Zoom room for the second keynote. So let me introduce the first keynote speaker. Fei Li will give us a talk on software hardware co-design for cloud native database systems.
Standard machine learning like techniques, like tree-based techniques. You may ask, like, why not deep learning?
Fei Li is currently a vice president of Alibaba Group, ACM distinguished scientist, president of the database products business unit of Alibaba Cloud, and director of the database storage lab of Damo Academy. He is a tenured full professor at the School of Computing, University of Utah. Yeah, he has won multiple best paper awards, including the ACM SOCC 2019 Best Paper Award runner-up, and IEEE ICDE 2014 10 years Most Influential Paper Award, and the Sigma 2016 Best Paper, ACM Sigma 2015 Best System Demonstration Award, and ICDE 2004 Best Paper. And he has been doing a lot of services, including PC co-chairs and core committee members for many prestigious journals and conferences. Let's welcome Fei. I'm going to stop sharing, and Fei is going to share his screen. Hi, Fei.
All right.
Can you share
screen? Yeah, thanks, Shimin. Thanks for the introduction. Thanks for everyone for tuning in. And let me try to share my screen. I hope this works.
I would like to say a little bit, a few words. So during the keynote speech, everyone can post a question in the chat box. So I'm going to collect the questions and ask them after Fei finish his presentation on behalf of all the audience.
Okay, can everyone see my screen? Everything is okay?
Yes, I can see.
Okay. All right. So, do you see the full screen or do you see the PowerPoint in the presentation mode?
In the presentation mode, I see.
Okay. So are you seeing the full screen or showing the presenter mode?
It's the present.
We actually can see the presenter mode.
Okay, now it's the full screen mode, right?
Yes.
Right? Okay. All right. Okay, the first time I'm using Zoom for doing a presentation like this. Okay, great. Thanks for everyone for joining this workshop, and it's my honor and my pleasure to be invited to give this talk. So as Shiming has introduced, my talk is about software hardware co-design for cloud-native database systems. So without further ado, let me get started. So here is the outline of my talk. So I'll give the audience a quick background of cloud-native database systems. Then using two particular systems we have been building at Alibaba Cloud to demonstrate the importance of software hardware co-design for building cloud-native systems. That will share some concluding remarks at the end. So we all know the evolvement of database system. This is a very typical view of how database system has evolved over the past 40 or so years. We started with structured data and relational database management system for transaction processing. Then as data keeps growing, then we and the challenge of dealing with read and write conflicts and answering the challenge from complex OLAP operations. We also built a data warehouse system where we use the ETL to transmit data out of OLTP system into OLAP system, where we can do complex OLAP operations. But in today's data processing applications, we are increasingly faced with heterogeneous data, from structured data to graph, to text, to time series, to vector. And we see the needs for building multi-model and H-type systems. So oftentimes we call this system as NewSQL database systems. Oftentimes in these systems, we need to take a hardware-software co-design approach to leverage the properties from the latest hardware vendors, such as RDMA, Open Channel SSD, NVM, GPU FPGA. So in my talk today, I will briefly went over some of these hardware techniques that have been put forward by different hardware vendors, and how we can leverage those hardware properties to design better systems, to better utilize the properties exhibited by these new hardwares. So I will give you a little bit background of what we do at Alibaba Group. So Alibaba Group is a complex ecosystem. Broadly speaking, can be classified into these categories, from digital media and entertainment to the core e-commerce operations, to local services such as map and other logistics services. And the backbone and the infrastructure for supporting all of this is Alibaba Cloud. So Alibaba Cloud not only provides the cloud infrastructure for all the operations within Alibaba Group, but also provides cloud as a service for external customers. So using the Singles Day as an example, Singles Day is an annual shopping festival organized annually on November 11th. So this is the real curve from November 11th of 2018. So you can see the workload stress on the database system has gone up by more than 122 times in less than 1 second. So the system, the database system behind the thing, supporting application as such, has to be designed with high availability and elasticity in mind in order to scale up to support workload like such, which explodes by 122 times in just 1 second. The number from last year, from 2019, is that the amount of workload, transaction per second, coming to our database system has exploded by more than 130 times in less than 1 second. So here is a collection of customers on Alibaba Cloud using our database services, ranging from finance to retailer to manufacturer to media and entertainment to many of them are well-known international clients. So in terms of database revenue, Alibaba Cloud currently rank at the 3rd place. We are after Amazon and Microsoft. This is a report by Gartner. And in the cloud market, we actually have surpassed Oracle and Google in terms of cloud database revenue. So our objective is to always to do more with less. When I mean more, we refer to more available, more secure, more stable, and more scalable, and using less resources. These resources refer to both human labors as well as machines. And this is really to support different kind of workloads we have to support from both within Alibaba Group and our customer on the cloud. So we have to support such different types of workloads. We actually have adopted and tried different database architects, which I actually discussed in details in a VLDB 2019 paper where I gave an industry keynote talk. So typically we have these different database architectures to choose from. We can choose a single node setup like what is shown on the left here. In this slide, by the way, the DB box refer to the bundle of CPU and memory together. So this is the typical design adopted by MySQL, PostgreSQL, and the traditional or commercial database systems. But increasingly, we see the increasing interest in so-called cloud-native database systems, which is shown in the middle here. First proposed by AWS Aurora, and then we have taken a similar approach and designed a system called POLARDB. What POLARDB does is to decouple computation from storage, as you can see from here. So it uses RDMA to build a shared distributed storage and decouple computation from the storage node down below. And as a computation layer, it uses a share everything approach. And in the storage layer, it uses a shared storage approach. We do have another approach, which is the traditional distributed database system approach, where you have a share nothing layer, then you have many different shards, where each shard is a single node instance setup. So this is really to support horizontal scaling out. And we have also designed the distributed version of POLARDB called POLARDB-X using this particular architecture. And we also have an OLAP system called AnalyticDB using a very similar design as such. So that's enough background. Now, in the remainder part of my keynote today, I will talk about, there are many things we can talk about in POLARDB and ADB. But what I want to focus in today's talk, given the theme of this workshop, is software hardware co-design in POLARDB and ADB. How we leverage properties of the hardware to accelerate computation and processing inside POLARDB and ADB. That will be the focus of today's talk. So some of the highlights before I get started is POLARDB is designed in mind to support excellent elasticity with low cost, high performance, and providing continuous solution for database applications on the cloud. So storage plays an important role in database enhancement. Storage is important for QPS, TPS capacity, RO instance extension, read-only instance extension, and fast backup. And the way we have done that in POLARDB is to use a design called PolarFS, Polar File System. It delivers extreme high performance with high reliability for cloud database by adopting RDMA network to build a shared distributed storage. And in the way of doing that, we have adopted OS bypass and zero copy techniques, as well as a parallel RAF protocol to allow three-way replica write latency to be compatible to a single replica on a local SSD. And the distributed shared storage architecture, in order to make it work with existing MySQL or PostgreSQL kernel, we make it POSIX-like user space interface, so that you can easily get a MySQL kernel talk to PolarFS, just like when MySQL kernel use MyFS talk to inNear-DB, so that from the kernel layer, it doesn't really need to be aware of the difference between a distributed shared storage versus a local storage. So that's some of the highlights we have done in POLARDB. Here is the architecture of POLARDB. as you can see, we use RDMA to build a distributed shared storage and decouple computation from the storage layer down below. And all the data coming into PolarDB are stored into what we call data trunk. And the data trunk is, each data trunk is three-way replicated using a parallel raft protocol, so that high availability is provided by default. And in the computation node, we have one write node, which is also called the master node, and we have many read-only nodes, so that as the workload, depending on the workload requirement, we can scale up or down the number of read-only nodes to provide the necessary support to enable high performance application running on top of PolarDB. So here are some quick numbers that you can see that a single instance of PolarDB can support capacity up to 100 terabytes, and you can read up to 1 million QPS, and the read latency is less than 1 millisecond, and it offers a very high availability and reliability using its parallel raft protocol as well as the distributed shared storage design. So some of the software hardware co-design principles we have adopted in designing PolarDB is highlighted below. First of all, to ensure low latency in terms of query processing and write processing, we utilize pure user space IO stack. And we do zero copy using RDMA. And we, of course, rely on RDMA network interfacing card to deliver so that we can ensure that a remote RAID is as efficient as a local RAID. We also use NVMe SSD and Optane SSD to accelerate the access to the storage layer. And in the computation node, we have active read-write and active read-only design. In other words, the master node is so-called the primary node, handles all the read and write, and all the other nodes are read-only nodes. Of course, in the next generation of PolarDB, we will design a multi-master approach where all the nodes can handle read and write, not only the primary node, so that we can get rid of the bottleneck of the primary node when there is an extremely large amount of writes coming into the system. And at the storage layer, we have three-way replicas using parallel raft to ensure high availability. So here is a more detailed examination of PolarDB's architecture. As you can see, in the computational layer, using one physical machine can actually have multiple virtual machines or containers to run multiple instances, read-only nodes of PolarDB instance. In other words, each read-only instance doesn't really have to be running on in isolation on a single physical machine. A physical machine can have multiple VMs or containers, each containing a read-only instance. All of them are accessing the same shared distributed storage down below. So this actually reflects another popular design nowadays in cloud-native systems, which is so-called the serverless design. In this approach, we have actually achieved serverless storage by decoupling the VM and containers from the storage engine down below. So we also have a Polar proxy at the front end, so that the Polar proxy can do things as dispatching write to the master node and dispatch read requests to read-only nodes, as well as to do load balancing between all the read-only nodes. So so here is a more detailed look at how PolarFS comes into the picture here. So PolarFS, as I mentioned, is a distributed file system that present a POSIX-FS look interface to the kernel above. And then a PolarFS talks to the distributed shared storage down below. So, and it achieve all the stuff I talked about just now, the software hardware co-design property I have mentioned, such as zero copy, user space stack, user space IO stack. All of those are done using the PolarFS abstraction, so that the kernel layer, such as the query optimizer, query execution engine, they don't have to worry about all of this. They talk to the PolarFS just like MySQL using MyFS talk to inNear-DB. It's very similar. In a very similar fashion, they can talk to PolarFS, then talk to the shared distributed storage down below. So here is a more detailed examination of the PolarFS architecture, which is available in a VLDB 2018 paper. So you have 4 key components: a libpfs, a polar switch, chunk server, and the polar control. So here is a quick examination of how it works. Essentially, the polar switch is responsible for switching requests to different trunk servers, and the libpfs is the library running in the kernel, so that the request from the database kernel is handled by libpfs to the polar switch, then all the way to the trunk server down below. And all the trunks in different trunk servers are managed by the parallel wrap protocol to ensure that we have that 3-way replica to ensure high availability. So that's a high-level overview of what's going on inside PolarFS. For more detailed examination of this, please refer to the VLDB 2018 paper. Now, so that's enough of PolarDB and how it leverage RDMA to achieve, and some other software hardware co-design techniques such as zero copy and others to achieve decoupling of storage and computation and give you a cloud native design with a serverless storage engine. The benefit of that is obvious, right? Because now user can have much better elasticity than the traditional approach where storage and computation are tightly coupled together. Now I can scale out my storage and or my computation independent of each other on demand, which is really nice for cloud applications. But what about, what if I want to do analytical processing inside PolarDB? Let's look at what's going on. So in PolarDB, because we decouple the storage from the computation node, right? The computation node, as I mentioned, has CPU and the DRAM bundled together. And they talk to the storage node through the network, because now we're no longer talking to a local storage device. We're talking to a network storage device, shared distributed storage engine, right? So the transaction workloads coming all the way from CPU to RAM, going through the network and then going to the storage node. For transaction workload, this is fine because transaction workload refer to write, insertion, update, and maybe a very small amount of point query and range scan with small ranges. But what if you want to do some, a little bit more complex analytics, such as a range scan with a fairly large range? Then that will create a lot of traffic, going back from the storage node all the way to the network, to the memory, and then to the CPU. This is especially the case when we are using shared distributed network storage. Let's look at a table scan, for example, right? The idea is actually quite simple. If we have a storage node that can do some simple computation for us, which I will talk about how we do that later on. But suppose we do have a storage node with some computation capability. Can we push down table scan operators all the way from the compute node to the storage node, so that the CPU contention and memory pollution problem are no longer an issue for the compute node, and we can deal with those in the storage node. So the idea is to do the following, right? So one idea, one may argue, okay, you can use an accelerator such as FPGA or GPU, right? And you distributed storage is still using SSD. Okay, this is the design as we highlighted here. Okay, so you can offload, for example, the table scan operation, those computation to the accelerator. But the problem with this approach is you have to transfer data from SSD to the accelerator, to the FPGA or GPU, in order for you to do the offloading of those computation. That will create high data traffic between those storage node and this centralized computing node. You will still have a compute hotspot for that accelerator, unless you are willing to use a lot of those accelerators. So that's still quite expensive if you consider the peer-to-peer PCIe data transfer between those storage nodes to the offshore accelerators. So can we do better? So one idea is to leverage the so-called computational storage drive, in short CSD. So this, if each storage node come with some limited computational power, then we can do what we call distributed computing within those storage nodes. And this also eliminates the so-called compute hotspot in the earlier attempt of using an offshore accelerator to do it. And this will also reduce the data traffic throughout the stack. So that's essentially the high-level idea. So let's see how we do this. Computational storage is not really a new idea, right? In the past 20 also years, it has surfaced with many different forms, such as intelligent RAM, active disk, intelligent SSD, smart SSD, and you name it, right? So there are many different companies have tried out this idea before. So what's new here is we see a reinvented interest in this simple idea. So for example, in last year, there is an internal draft organized by this group of companies in Storage and Networking Industry Association, where they try to push out an industry standard for computational storage architecture and the programming model. So the simple idea is to enable some simple computation within the storage, right? So how do we do that? So this is a high-level idea of what's going on, right? So we have a line, a boundary, the blue line, as you see from this slide, that indicates the boundary between software and hardware layers. So the idea is, if we can have a single FPGA attached to the flash controller, the NAND flash controller, then the SSD device will be able to do some simple computation for us, such as inline compression and depression, and simple filter logic maybe. Then in the file system layer, we can have a CSD driver, computational storage driver, to talk to the CSD with such capability. Then the higher layers, the database kernels talking to the file system, like POSIX-FS like interface, will not they don't even have to be aware of the change down below, because all of these are abstracted away through this file system layer. So that's essentially the high-level idea. And we have done some simple experiments with comparing CSD with NVMe SSD with a mixture of read and write performance. As we can see, by the way, the y-axis is IOPS. So as we can see, across the stack, CSD can achieve better performance than a standard NVMe SSD drive. So So let's look at this design in more details. So look at this picture right here. So as we see, you know, without a CSD, the traditional approach we have is a picture shown here, right? We have a SSD flash disk with flash controller and NAND flash storage, and all the, you know, SQL processing, data scan, and compression, decompression happen at the software layer within the database kernel. What if we have a computational storage drive? Then we can push down data scan and into the storage device inside the hardware, so that the software focus on only the so-called intelligent or more complex SQL processing, and a lot of those additional computational overheads, such as, you know, brought by data scan and decompression and compression, can be offloaded to the computational storage drive. So that being said, let's come back to this picture, which we have seen this a couple of slides back. So this essentially is the general idea. Now let's see how we realize this idea inside POLARDB. So we team up with Scaleflux, which is a company based in Silicon Valley, and they produce this so-called computational storage device, as you see from this slide right here. Working with Scaleflux, we investigated how we can leverage a computational storage device such as Scaleflux SSD with POLARDB. So POLARDB is, you know, particularly in a particularly good position to do this because of the decoupling of the storage layer with its computational layer, right? So what we have done is the following. We focus on, for example, the table scan operator. So the idea is, you know, so we have these few components: the analytic engine inside POLARDB, the storage engine, the file system, the device driver, all the way to the CSDs. So the idea is we can push the table scan all the way from the analytics engine to the CSDs. So here is, you know, the inside of the Scaleflux CSD. Yeah, essentially, it uses a simple FPGA to achieve limited computational support within the storage device. So how do we do this? So the idea is from, you know, the inside the POLARDB kernel, from table scan requests, and using the PolarFS and PolarDB storage engine, we figure out the data location, the offsets in files from the storage device, and the table schema and the scan conditions. And we are using a log structure merge tree for this purpose. Then we pass on those information to the file system and figure out the per drive scan requests, such as data location, table schema, and scan conditions, and then forward those to the device driver inside the CSDs. So those requests being forwarded to the device driver inside CSD will figure out, you know, address translation, scan condition reordering, request partitioning, FTL coordination, and then eventually they will send this scan request to the CSD. And once you are inside the CSD, this is the implementation within the Scaleflux CSD. Has a NAND flash with 16 channels to the flash control, and has, you know, has a couple of process engines using Z-Link's 16 nanometers FPGAs. So this is, you can imagine this process engine as oftentimes referred to as compute unit or CU within a FPGA. So then they are using PCIe to connect to different I/O interfaces. So essentially, you know, we are using FPGA hardware utilization, data path pipeline, as well as parallel batch processing, as we typically do when we are doing computation on FPGAs. Some of the optimization that we have done is block by block iterative processing, look ahead batch processing, mix of synchronization and asynchronous, you know, change synchronous synchronous call to mix of synchronous and asynchronous calls. And the details of some of these optimizations, please refer to the FAST 2020 paper that have talked about all of these details. So I will show you some experimental results before I move on to, quickly talk about AnalyticDB, and then I will give you the conclusion of today's talk. So here are the experimental setup. We are using the TPCH benchmark with varying degree of data selectivities. Okay? And we support snappy decompression and this set of scan conditions. These are the IPJ we're using, the flash we're using, the PCIe we're using, and other configurations that we use in the experiment. So this is so let me skip the unit test. Let's look at this figure right here. So as we can see, the purple bar refer to the CSD-based scan with snappy decompression. As you can see, across all different workloads, CSD-based scan achieve the best performance compared to other approach. In these two figures, we are looking at data traffic from the PCIe interface as well as main memory data traffic. So now, surprisingly, when we are doing the pushing down of the scan all the way to the storage device, we obviously will be able to reduce data traffic across the stack. So the reduction in data traffic in return brings down the query latency, as we see from this figure right here, by comparing different approach as we have highlighted here. So, 11 queries, we have seen more than 30% latency reduction, and query 7, we even see more than 50% reduction. It all depends on selectivity of the query, right? As you can imagine, the more selective the query is, the more benefit you are getting out of pushing down the table scan and filtering condition to the storage device, to do that within the storage device using CSDs. So there are some other experiments. I think I will skip this one. This is to show you all the different queries in TPCH essentially. Okay. So this is really a summary of what we have done with CSD and POLARDB. Okay. This is, I think, a good example of using software hardware co-design principles to improve the performance of cloud-native database systems. So we are also looking at how we do this for the distributed version of POLARDB, which is POLARDB-X. In particular, we have a storage engine called X Engine. And also in FAST 2020, we talk about how we use IPJ to offload the compaction operation within X Engine to speed up the compaction and data reorganization process inside X Engine. That's another example of software hardware co-design in cloud-native database systems, which I don't have time to go over today, but I encourage you to go look at the paper in FAST 2020 from our paper in FAST 2020. Okay, so that's the part on POLARDB. I will use another 10 minutes also to talk about ADB and conclude my talk. So ADB is a high-performance OLAP database system at Alibaba Cloud. So it's similar to POLARDB, and it also leverages a cloud-native design by decoupling the storage layer with its computational resources. In particular, we utilize Pangu distributed storage system, which is a distributed storage developed at Alibaba. And then we have a scheduler called Fuxi that manage all the computational resources, CPU and memory. And then inside POLARDB, we have write node, read node, and coordinator node. And the scheduler is responsible of dispatching computational resource, CPU and memory, to different worker such as writer and reader and the coordinator. And it's a serverless design because it decouples the storage and the computation, just as we have done in PolarDB. The difference is ADB utilizes a share nothing distributed approach, whereas PolarDB utilizes share storage and share everything design as a computational layer. So here is how we do table partition inside ADB. I don't think I want to go into detail here because this part doesn't really have a stronger connection with software hardware co-design per se, but the next one does. So essentially, one of the important property that we are trying to enhance in AnalyticDB in a cloud-native OLAP system such as ADB is to ensure that we can support high throughput of insertions into ADB after the initial bulk loading of the initial set of data. So the use case is as follows, right? For a data warehouse application, you want to do bulk loading for the initial set of data, but then you also want to make sure that you can continuously incorporate new updates from the original data source, right? So this requires us to do a Lambda storage design as highlighted here. So we have the baseline data with index and all the detailed storage layout on the distributed shared storage. But then how do we deal with those incremental data coming in? So the way we have done that is to use a Lambda storage architecture. We use bitmap to mark the part of data that's being deleted and the part of data being updated. Then we do minus and the union with the incremental data and the baseline data. And the way we have done this is to use, first of all, SSD, and we have started experimenting with NVM so that we don't have to worry about complex crash recovery process for this part. And then we use IPGA to do to offload this process to the IPGA so that we can free our CPU resources. So that's another very good example of software hardware co-design that can help cloud-native database systems. In this particular case, we're using this to speed up the merging process so that we can have high throughput of insertions when we have updates from the original data source to the baseline data that already exists within ADB. So here is an index structure in ADB. I will skip all of this because this doesn't really connect with the main theme of today's talk, which is hardware software co-design. ADB also features with a hybrid row columns store so that it can process analytical queries really efficiently. We have some experimental results. We are using standard benchmarks such as TPC DS as well as real query workflow as such, and we compare with PastoDB, Spark, Greenplum, and Druid, and the detailed results are available from our VLDB 2019 paper from last year. So you can, if you're interested in learning more details, you can refer to our paper from last year's VLDB. Okay, so that's essentially, what I would like to share today with you, how we do software hardware co-design and apply that in cloud-native database systems. I'm using OLTP system and then an OLAP system as an example to demonstrate those ideas. Here are a list of recent publications from our team. Many of the topics I went over today are available from these publications. You can refer to those papers for more details. So conclusion. So cloud native means that our system needs to be more elastic and offer high availability and excellent scalability. And oftentimes this requires us to decouple a resource stack. For example, decoupling the storage from the computation layer. And then even we are looking at, in the next generation, we are looking at even to decouple memory from CPUs. And then we increasingly see the needs of HTAP, supporting hybrid transaction and analytical workload in one system. multi-model to deal with different data types and data structures. And oftentimes, all of this require careful examination and the leverage of new hardware support using a software hardware co-design principle. Some other topic I don't have time to go over today that's super important for cloud-native database system is security and using AI and machine learning technique to make the database system like a self-driving car. We call that self-driving databases. Those are the topic I don't have time to go over today. So with that being said, that's all I want to share with you today. Thank you so much for your attention, and I'm happy to answer maybe 1 or 2 questions if time permitted. Thank you.
Thank you. We actually have 5 minutes for question. And okay, I got one question. Feifei, can you please elaborate on HTAP?
Okay, yeah, definitely. So that's a very good question. So in cloud-native database system, the typical setup nowadays is to you get a transaction processing engine such as POLARDB. But even with the software hardware co-design approach that I have introduced today, for example, by leveraging a CSD, computational storage device, you can support simple analytical operations such as table scan, but you are not able to do complex OLAP operations like join over multiple tables with wet columns because the fundamental barrier of the conflict between read and write. So what we do is to transmit data from a transactional engine to an OLAP engine such as ADB and synchronize data in real time. And that's why we talk about in ADB how we can do this Lambda storage to merge incremental updates with baseline data. But what if we can do all of this in one system without moving data around? Wouldn't that be super nice? So, I really do believe, that will be an interesting challenge to address in the next few years. The way we do that, I believe, the traditional approach, like if we look at SAP HANA, what they have done, they try to design a hybrid row column storage engine in memory approach, but still the conflict between read and write and the data shuffling between moving row store to column store is still very expensive. So one possible solution to address this, in my opinion, is to leverage the high availability that almost exists in all database systems nowadays, right? Typically, you are using Raft or Paxos protocol to replicate data 3 ways to ensure high availability. So why not, in that process, when you're doing high availability data replications, you replicate data in a way such that you have 2 replicas in row store, then the 3rd replica is in column store. Or maybe 3 replicas are all in row store, but you add a 4th replica, the 4th replica in column store. So that then, using a smart proxy, you can dispatch complex OLAP operation to that replica with a column oriented storage to do your OLAP processing over there. So in my opinion, that might be a good solution to address the HTAP challenge. So that's something we are exploring as well at the moment.
Hi, can I ask a question?
Excuse us. If you want to ask a question, please just type in the chat window, and I will be the moderator. Which
architecture do you use for HTAP Polar? So this is good. So we actually are exploring from both directions. Inside PolarDB, we're trying to do HTAP using PolarDB's read-only node, but we are also using AnalyticDB to do HTAP because both PolarDB and AnalyticDB are using Raft to do high availability. So we're experimenting with the idea I have just mentioned, which is, among the replicas, 3 replicas are row-oriented, but the 4th replica, maybe we will do that in column-oriented fashion so that we can do HTAP. In ADB, but their focus is there is a slight difference in terms of the focus. PolarDB, the primary objective is still to ensure high performance transaction processing. And ADB is still, the primary focus is to ensure high performance complex OLAP processing. So they are both trying to do each step, but the focus is slightly different. So I hope that answers your question over there. Architecture of PolarDB and so PolarDB and AnalyticDB are available on our papers. So if you can look up these papers, you can find the details of the design of PolarDB and ADB. So ADB, for example, is available from the VLDB 19 paper, and PolarDB you can read the paper from VLDB 18 PolarFS, as well as my keynote talk paper from last year in VLDB 19, Cloud Native Database Systems. And some of the topics I went over today are from our FAST 2020 papers. So maybe I will answer one more question.
So there's a question about the hardware software code design. Basically, what will happen if the selection conditions become very complex?
Yeah, that's a very good question. I think Marco's question and Sammy's question are similar, right? In some sense, we you know, the stuff I talked about today, leveraging CSD, the idea is still in the early stage, right? So in the paper, we demonstrate how to do this for table scan. We don't really have a good answer for complex query workloads yet. And what's the impact to the query optimizer if we try to do that, right? So far, we focus on simple table scan and some other basic operator we talk about in the paper. But take table scan as an example. If we only talk about table scan, then the choice is very simple. It boils down to, as Samus has rightfully pointed out in the question, essentially, if you look at only table scan, then it boils down to a selectivity, right? If your selectivity is high, meaning that you are pruning away a lot of records, then it makes sense to push down this to the CSD. But if your selectivity is low, meaning that you're not pruning away many records, then it doesn't really buy you much by pushing this down all the way to CSD, right? So if you only have table scan, the answer is a clean cut, right? All you need is a good query cost estimator to estimate the selectivity of your queries. But if you have more complex queries, like Marcos trying to ask, right? Like if you have a complex query workload and using the traditional CBO cost-based query optimizer, how do you decide what to push down to CSD, what to be done still within the traditional kernel space? The answer to that is not clear. We haven't investigated that in full details yet. But that may be a good question to follow up as a follow-up research work, I think.
Okay, I think our time is up. So thank you for the excellent keynote. And we're going to switch to the next session. And June will chair the next session.
Hi, everybody. Well, I'm the TC chair of the SMDB workshop this year. And for the next talk, we will have Guoliang Li from Tsinghua University. And he will talk about something about the AI native databases. And Guoliang Li is currently a full professor of the CS department of Tsinghua University. And his research interests include AI native databases, big data analysis mining, and cross-source data management and spatial temporal data analysis. And he has already published more than 100 papers. And I believe that's where you have already seen his name in all kinds of the conferences like the IC, VLDB, and Sigmod. And where he also definitely worked on for the as a associate editor for the attribute transactions and the data engineering and VLDB journals and some others. And he also gets several best paper awards like the CLKM and ICD and KDD and DASFA. And he's also the recipient of the VLDB Early Research Contribution Award and the IEEE TCDE Early Career Award. So, well, I don't want to occupy too much time to introduce the Guoliang, because I think his talk will be very exciting, and he will definitely give us a very wonderful talk. So Guoliang, can you just start?
Yeah, thank you, Yinjun, for your introduction. So can you see my slides?
Yes.
Yeah. Good morning, everyone. So it's my pleasure to give a talk in the workshop. And today I will introduce AI native database. And Feifei also mentioned that the self-drawing database. So the idea is similar. So on one hand, we want to utilize AI to automate database. For example, the traditional database usually rely on some heuristic, for example, for cost estimation, and for the joint order selection, and for the knob tuning. And all the current techniques usually rely on the heuristics. So we can utilize AI techniques to automate database. So we can see that in recent 5 years, there are a lot of work on using AI techniques to automate database. On the other hand, we also want to utilize the database techniques to automate AI. We know that AI has longer history than database, but there is no very popular system which as popular as database. And we know that database is very popular and widely used in every domain. So the AI is rather hard to use. So can we use the database techniques, for example, some declarative queries and some automatic techniques to reduce the burden of using AI? So this is the DB for AI. So today, I will introduce the recent techniques that for AI for DB and a database for AI. So I first give the motivation of why we want to start AI native database. So today we are in an intelligent era, and we call for more intelligent database. For example, in many data centers, there are more than 10,000 nodes in the cluster. So how can we to maintain the cluster, and how can we to tune the database, especially the cloud database, as mentioned by Feifei? So we need to more intelligent methods. And we also have lots of works, for example, AI ops. I think in the second keynote, and the guy from Oracle also will mention some AI ops. So can we use the AI to help us to manage the cluster and help us to monitor the cluster, and to, for example, for some bugs, can we to do some self-healing and self-management? So this is the first motivation. The second motivation is that we know that there are lots of databases. So we can see the websites of maintaining the database leaderboard, and there are more than 300 databases. Why do we have so many databases? Because for each scenario and for each data type, we need to have a database. For example, NoSQL database, and some document database, key-value database, and some Relational database, or TP database, and or AP database. So we have lots of databases. So can we have AI native methods that for each scenario, we can design very effective database that more optimal for this scenario? This is the second motivation. The last motivation is that we have lots of diversified computing resources. For example, we have traditional CPU and GPU, and recently we also have some AI native hardware. For example, some TPU and some very new hardware. Can we utilize the new hardware to optimize the database and to optimize the AI? So later I will introduce, we can combine AI and database. For example, we can extend the SQL to support the AI operations. So in this way, we can use a single system to support both AI and database operations. So this is the third motivation. So we can say that there are lots of opportunities and lots of challenges in AI4DB and DB4AI. First, for AI4DB, and the goal is that the training database is very manually, and we want to make the automatic database. So later I will introduce, for example, self-automation, and we can use AI techniques to automate database, and self-configuration, for example, the knob tuning and the buffer tuning and the buffer replacement strategy. And for example, for self-monitoring, how can we monitor database and how can we to do some self-healing? And also, we have lots of work on self-security. For example, how to detect the attack from the users and how to protect the database. And lastly, I will introduce some work on self-design. So how can we to use AI to design some database components, for example, Estimator, cost estimator, and how can we build a database by AI techniques. So this is AI4DB. For the second one, the DB4AI, so our goal is that to make AI is as easy as be used at DB. So this is a motivation. So we want to support declarative AI, so we can extend SQL to support some AI operations. And we also want to utilize database techniques to automate the AI. For example, in the self-driving, and we usually rely on lots of training data, but usually not many training data is better. And we only need the training data in the corner case. For example, the raining day and the dark day. So how can we utilize database techniques to help us to automate AI? And we also want to use some data governance techniques. For example, most AI scientists, most of their time will rely on some data cleaning. For example, they first get the relevant data and discover the data, clean the data, and integrate the data. And then based on the clean data, they can apply some models and try different models, try different parameters, and get the best models. So this is for data governance. And we also want to use, for example, some model management techniques, how to maintain the models and the model provenance and the model management and some auto ML techniques. And finally, I think we have lots of opportunities for the AI and database hybrid model. For example, the database rely on some relational model and AI rely on some tensor model, especially for deep learning. So can we propose a new hybrid model that can support both AI and database? So this is our goal. And we also want to support AI and the database hybrid inference. And later I will introduce some real scenarios. So we can say that under the first generation database, a single node database, and then cluster database and the distributed database, and Feifei also introduced cloud native database. And I think we can also have the lots of opportunities to build an AI native database. So this is the basic idea. So we can also, you may know that the self-driving has 5 steps, and we also introduce 5 steps for AI native database. So the first level is AI engine as a plugin, and we can provide some offline advisor. For example, we can provide some knob tuning. For example, for any database, Oracle, MySQL, and PostgreSQL, and if the database is running on cloud, and we say that the database is slow, so can we to improve the performance using some knob tuning techniques? So this technique can be utilized in any database, and this is the AI agent as a plugin, and we can also have index advisor. So how to build the index, and build index on which column, and view advisor. So how to build the views. So this is the first level. So we can take AI engine as plugin. So the next level is AI engine as built-in. And we can build the AI engines inside the database. And in this way, we can do some online monitoring. For example, we can monitor workloads, and we can separate the workload into, for example, the performance critical workload, for example, TP queries, transaction queries. And we can to postpone the AP queries, for example, the analytical queries. In this way, we can on the fly to monitor the database. And if there's some, for example, there's some query slow, we can directly to predict the workload and to rewrite some slow queries, sub-queries. And this is online workload modeling, monitoring, scheduling. So in this way, we can make the AI into the very critical systems in the database. So the second level is we want to build AI-driven components. For example, for some components, for example, the index and the Kraska from IMT to design the learned index. And there are lots of work on learned Estimator and learned cost estimator. So in this way, we can make the database more intelligent in many database components. So this is on one hand, we want to design AI-driven components. On the other hand, we want to support AI inside the database, and we extend the SQL to support AI operations. So we call it declarative AI, and we also need to support AI and database hybrid model and hybrid inference. So this is the second, the third level. So we want to support both AI inside the database and to make database components more intelligent. And the fourth level is that the AI-driven self-assembly. For example, for each database component, for example, for Estimator, we have the rule-based Estimator, cost-based Estimator, and the AI-based Estimator. And for storage, we have columns-based storage, and row-based storage, and in-memory storage. And we also have different index. So for each component, we have many alternatives. So can we to self-assemble these components to build a new database? So this is self-assembling. So we know that the traditional database usually depends on some architecture. For example, I am an architecture of a database company, and I can design database based on my experience and based on some other database we can design. But this design only based on some human knowledge. So can we use some intelligent knowledge? For example, use AI. So before AlphaGo, we know that human is much better than the machine for Go game. But after AlphaGo, we know that, okay, the AI can explore more space and can get much better the space. So it can beat the human in Go game. And in the database, we can also use some AI techniques to assemble a very good database for different scenarios. So this is the self-assembling. And we also want to support the inside database optimization, the AI optimization. For example, we use the database techniques to optimize AI. So later I will introduce some scenarios. And the last step is the self-design. So we can use AI to design database. I think this is a vision, and in the future we can to do some AI and database fusion. So next, I will introduce the 5 steps. So the first level is the AI advanced database. We can take AI engine as a plugin. So in this way, we can do lots of work. For example, for database configuration, we can support knob tuning, how to set knobs, and buffer tuning, and how can we set the buffer size. And we can also to use AI to do some buffer replacement strategy, and workload management, workload modeling, and SQL prediction, and slow SQL prediction, and slow SQL rewrite. So there's this technique can be used for any database, and because it is plug-in and can be used anywhere. And for database optimization, for example, how to build the index, because some users in class, they are not very familiar with this, and usually they do not know how to build the index and how to build the views. And for the for example, for the distributed database, and for example, share nothing base, for example, for Spanner, for TiDB, CrouchDB, they will to distribute the data into different partitions. So how to automatically to partition the data? This is also a challenge. So usually it's based on the human decides the partitions, but we can use AI to design the best or optimal partitions. So this is the first level. So I take the knob tuning as an example. For example, for different databases, for example, MySQL, Teradata, and MongoDB, there are lots of parameters, more than 400 and 500. So we can also to classify the knobs into different categories. For example, for file system, for the performance, for the I/O, for the optimizer. And how can we to select the best or optimal knob values? This is a challenge. So we propose deeper reinforcement learning-based techniques to address this problem. So the basic idea is that, for example, if we want to tune the database and we have a system, we call it the agent, and we also maintain some correlation between the knobs and the performance, and we use a deep neural network to capture the correlations, and we want to tune the knobs. This is the action in the reinforcement learning. So we can increase the knobs and we check the performance. For example, the performance can be quantified or evaluated by the throughput or latency of our service level agreements, SLA. So for example, if we increase the knobs, for example, effective cache size, checkpoint timeout, IO concurrency, and if we increase the value of a knob and we check the performance, and the performance is better, we can say that, okay, this is good tuning. So we give a positive reward. If we tune a knob and the performance become worse, we will give a negative reward. So this is the basic idea. But how to capture the correlation between the knob tuning and the rewards? We can utilize the database metrics. For example, the conflicts or the transaction commit rollback per second, and the bug reach and hit per second. And there are lots of metrics. This is very similar to, for example, if I'm ill, I will go to hospital, and hospital will get some metrics. For example, give some, for example, the blood pressure and some other metrics. And the base metrics, we know that, okay, how to tune the knobs. So we can say that if we tune the knobs, we know the metrics, the change of metrics, and we use the correlation to help us to predict performance. So this is a basic idea. So when we tune the knobs, and we can get the performance change, and we also know how the metrics change, and we capture correlation inside the deep neural network. So using the neural network, we can do some knob tuning on the fly and for online tuning. So this is a basic idea. So the cloud database tuner, or we call it CDBTune, and we use deep reinforcement learning techniques to do some end-to-end learning. And we only use a limited number of samples to do the tuning. And we can support the high-dimensional continuous knob recommendation. And we can reduce the possibility of local optimal. And our method has also very good adaptability. For example, when the hardware changes, when the workload changes, when the data changes, and our methods can support the changes. And we also study, for example, the schema change, how can the method to support the changes. So this is a basic idea. And this is a workflow for offline training. We build a training model and train the training model. And for online, we use a model to do some knob recommendation. And if you are interested in details, you can read our paper. So this is a workflow. For example, if the user finds that the database is slow and we want to use some knobs, and then the user will interact, or the client interacts with our component CDBTune, and our component will conduct some stress testing. For example, we will run some workloads in recent 5 minutes in the system, and we run the SQL queries and get some metrics, and based on metrics, and we can do some recommendation to recommend some knobs. So this is the workflow of our CDBTune, and I will omit the details due to the time constraint. So I will mention that for using reinforcement learning to design some database components, we need to design how to map database into the 6 key elements in reinforcement learning. For example, agent is our tuning system. For the environment is the database, for example, cloud database or some on-premise database. And the state is the database matrix. So database will monitoring some information, and this is state. And the reward is the performance change of the database. And action, for example, the action could be the knob tuning, or for example, join order selection, and we have a new join, or join A and B table or B and C table. So these are actions. The policy is the neural network to capture the correlation between some knobs or some states. So this is the design to utilize reinforcement learning to address some database problems. So we use a double stage neural network. So for this neural networks, we capture, for example, these knobs and this matrix, and this is the performance change and the reward. And here we can get the information based on some workloads. And for this one, this is for online recommendation. So this is a matrix, database matrix we have. And for here, this is knobs. So in the offline training, we can get some correlation between the knobs, matrix, and the performance change. And using this, we can get the online tuning. For example, based on matrix, we can recommend some knobs. So this is the basic idea. So there are some details on how to design the policy function, how to design the critic function, how to design the neural networks. And there are some details, and you can refer to our papers. And another challenge is how to design the reward function. And this is also very challenging in applying the reinforcement learning in database. So how can we get the reward function? So the reward function not only depends on the rewards between these steps and the last steps, but also depends on the current step and the initial step. So we need to design a very good reward function. So this is a basic idea, and we can get some results. So here are some results. We can say that with the number of knobs, we can get much better throughput. This is throughput, and this latency, the latency will decrease based on we tune more knobs. And this is a number of iterations for tune knobs. We can say that we can tune more than 200 knobs. And here we compare with different methods. For example, read-write workloads, read-only, write-only workloads, and we compare with traditional methods, and this is a tuning method, and this is DBA. We can say that our methods can increase the throughput and reduce latency. So we test our methods on lots of databases, PostgreSQL, MySQL, MongoDB, and our techniques also applied on Huawei Cloud. And there are many users use them on the cloud. So this is tuning. So for tuning, I mentioned that we tuning for workload. And we can also do some fine granularity tuning. For example, we can tuning the knobs for a single query or for a cluster of queries. So in this way, we need to do the query encoding and we to encode the query inside the base. So this has an advantage that we can do more fine granularity tuning. But the downside is that we can only to, for example, support the specific query. For example, for this query, we can automate. But for the whole workload, if we want to tune the parameters for all query workloads, we need to utilize workload level tuning and the query level tuning. So if we only support the query workload, like CDBTune, we do not rely on any query and any table. But for here, if we want to get better performance for a specific query, we need to encoding the query. So how to encoding the query and how to provide the query level tuning. So there's lots of challenges. And if you are interested, you can read our VLDB papers. And here we provide query level tuning, workload level tuning, and cluster level tuning. So the basic idea is that we can classify the queries. For the query in the same cluster, they should share the same knobs. And in this way, we can run the query in this cluster and get a better performance. But for queries in different clusters, so we can tune different parameters. So this is a basic idea. And this is some performance. I will omit the details. So next for the view advisor. So the basic idea is that, for example, for some queries, we want to automatically build views. So how to build a view? So firstly, we need to get some equivalent subqueries, and we will quantify the benefit and cost to build a view for such subqueries. So we need to estimate the cost and benefit. And based on the cost and benefit, we can do some view selection. So we have the paper talk, I think, at Wednesday or Thursday, and in the 23 session. And if you are interested, you can go to our paper session to attend our talk. So this is a basic idea. So given some queries, how can we build views? And I will omit the details due to the time constraint. So next is the second level. So the built-in AI. So we can do some self-monitoring. For example, we monitor queries to predict queries. And we do some self-diagnosis to, for example, if we detect some error, for example, the disk error, the memory error, CPU error, we can detect errors and do some diagnosis. So we can also do some self-healing. We can automatically recover from the failures and do some on-the-fly configuring. For example, the system upgrade. And for self-optimization, for example, SQL rewriter and online statistics, for example, we need to do some online cost estimation. So this is the architecture. For example, for database, we do some monitoring. For example, we get some metrics and we store it in the instrument information. And we can also to ETL the information into an information store. And based on information store, we can do some analysis. For example, for anomaly manager, for example, there are some anomaly, we can do some root cause analysis. And if we want to change the database, for example, the hardware change and some data schema change, and for the change, we can predict the performance. And we can also predict workloads, and for different workloads, we can predict performance. So this is a self-monitoring. So we can do some lots of work, for example, workload modeling, workload scheduling, and workload prediction. And we can also for example, help us to prioritize the workloads. And we can also automate the transaction queries. And for example, first run the TP queries and then run the AP queries. And if some queries have some conflict, for example, log conflict and data sharing conflict, we can to reorganize the query orders. So we have work on the performance prediction for concurrent queries. For example, we have lots of queries running together. So how can we to predict performance? So we use a graph embedding methods. For each vertex is an operator of a sequence, and each is a correlation between different operators. We have 4 types of the correlation. For example, the parent-child operator in a SQL queries, and the data sharing between the 2 operators, and the data conflict, and some resource competition. And use this, we can modeling the workload, and we can also to estimate the cost. So this is basic idea. So next, I only introduce some basic idea. I will skip the details due to the time constraint. For example, the learned database components, learned index, learned cost estimator, learned estimator, and learned statistics. So for example, how can we to estimate the cost? For example, we want to estimate the cost of drawing. And changing method use a bottom up and relying on some heuristics. And we propose end-to-end cost estimator based on deep learning. And we will have a paper in VLDB, and you can read the paper or to attend our talk in VLDB. And I will skip details. And for learned estimator, and there are lots of challenges. For example, join order selection. For example, give for tables, how can we get the best join order? So this is a very complicated problem. And for PostgreSQL, we have more than 10 queries. They will use some heuristics. And if we have a limited number of SQL queries, tables, they will use some dynamic programming. And we propose a learned estimator. So we will have a talk in SADE in our, I think, 27 and in a Thursday. And you can go to our talk to get details. The basic idea is also using the reinforcement learning. I also mentioned that, for example, for each action is a join. And for the reward is the, for example, if we have a join, how about the cost reduction? So in this way, we can train the model and utilize it to support the join order selection. And here we have 2 very good advantages. The first that we can support the schema change. The second that we support the alias for the tables. For example, table production as P, table production as P2. We can support the table name alias. So here I skip details. And the next declarative AI. So for example, how can we to support AI by extending SQL and to AI automatizations and to do some data governance. And here's a running example. For example, we have 3 tables, patent P and doctor D and operation. And the doctor will give a 30 for the patent. And we want to select a male patent who may stay at hospital larger than 7 days. So we need to have a prediction model. We also have a database operation. So how can we support such queries inside the database? And we need to design new AI estimator, database estimator, and database estimations. So this is so the first level is that to how to assemble different components to assemble a new database. So for example, for each component, we have different options. So how can we select the best path from parser to the storage? So this is cell assembling techniques. It's very similar to the routing on the map. So you can imagine that before we have the map on the flat map, how can we to, for example, to navigate? So this is a similar idea. So the last level is the AI design database. We can integrate the relational model and the tensor model to co-design AI and database. And this is the architecture. And we also have a paper on attribute data bulletin. And there are 5 levels, VLDB, and 5 levels of DB for AI. So some lesson learned. For AI for DB, we can say that database can learn from internal as external environment to achieve high performance. And we can utilize AI to enhance database. And for DB for AI, we can enable inside database AI opportunities. And we can to provide inside database AI consumability. And we can make AI easily be used in different fields. So this is my talk. Thank you for attention, and thanks for joining my talk.
Yeah, great talk. Thanks, Guoliang. And we have, let's say, probably 3 minutes to take any questions. So I think we got at least 2 questions. The first one is actually you mentioned that for the CDBTune uses the last few minutes of workload to train a model, then make recommendation, right? Is this intended for online tune?
So usually we have 2 or 3 stages. The first one is for the offline training. For example, if I'm the database provider, we first to train the knobs in the company, and then when POC, we will use the query workloads of the customers to retune the, for example, retuning or to fine tuning the knobs. And the third stage is that on the fly to retuning the knobs. I think there's 3 stages for the training.
Okay, so a follow-up question from me. Well, I'm not sure whether the training time will be a concern because for the that's where the workload can be different or the machine can be different. So it can take a very long time to train a model. Where I don't know in your case, but is that a concern for your methodology?
You mean for different hardware? If we change hardware?
Yeah, let's say different hardwares, different workloads, and different environments, different settings, basically. Is there any special concern about the training time?
No, so you can read the paper. So we also try, for example, we to change the hardware. For example, increase the memory size, increase the CPU cores, and our methods can adapt to the different environments. And because the reason why we can adapt to different hardwares, because for when we tuning, we also embed the hardware information into our tuning model.
Okay, great. Okay, so thanks, Guoliang, and I think we need to wrap up. So we have already had a very 2 exciting talks from Feifei and from Guoliang, and the next okay, so that's a short talk between SMDB and the HubBD. So after this session, please, the SMDB audience, please join the SMDB room because we have the session held there. And for the other audience, please just remain in this room. It's fine. Okay. So for the slides, I think Guoliang and will share the slides, and we will also post on our website. Thank you.
Okay. Okay, thank you.
Hello, this is Kuzaima Daoudi. I'm a co-chair for RBD Active research session. And we're going to take a couple of minutes break before we start the research session talks. Thanks. All right. Hello, everyone. My name is Kuzaima Daoudi, and I'm a co-chair of RBD and Active. We're about to start our research session. It's an exciting set of papers, solid work. All the papers have done a great job in covering the different areas. So our first paper will be on near-data processing systems. And the presenter will be Tobias Vinson. What we'll do is we'll run the video. And either while the presentation is running or at the end, please feel free to post questions on the chat box, and I will then direct them to the speaker. Thank you, and here we go. Brian, if you can roll, that'd be great. Thanks.
My name is Tobias Finson, and I'd like to introduce you our paper on the necessity of explicit cross-layered data formats in near-data processing systems. This is a collaborative work between the TU Darmstadt and the Reutlingen University, and is co-authored by Arthur Bernhard, Lukas Weber, Andreas Koch, and Ilya Petrov. First, I'd like to introduce you our research problem, which is based on a classical database connected through a bus system to a storage. As we have seen in the last decades, data volume is growing exponentially, as Jim Gray already said in Science is an Exponential World, by trends such as social media or IoT. This data is stored in the storage architecture beneath the database and has the property to has a very low data locality. This is because it's ingested very fast. So queries cannot expect to have all necessary data at one place, but distributed across the entire storage. Furthermore, we have seen a rise in analytical queries besides the OLTP workload, which is still available. So both workloads result in many point queries and scans, which are processed in the database. However, as they need the data, which has a low data locality, they also require massive data transfer between the database and storage. This is mainly because our current computer architecture is based on data to code, which means all the data which is processed by the database have to be retrieved from the storage and transferred to the database. Yet, our current bus architecture has a scarce bandwidth, which is then, of course, the bottleneck. So the massive data transfers on the exponential growing data sets impair the performance. But how can we fix this problem? One way to do it is, instead of executing the point queries and scans in the database, we could push them down to the storage and execute them as near-data processing queries by shifting the paradigm from data to code to data. So the processing logic is pushed down to the storage where the data is already available, and only the result sets are transferred back to the database or even the application. Furthermore, if we have a deeper look into the storage, nowadays advances in semiconductor industries made it available that we can place several processing elements on the same printed circuit board, chip, or even chip. And these processing elements could include, for instance, ASICs, FPGAs, ARM cores, and you name it. And these are connected to several flash NVM chips, which can be accessed independently. So the on-device bandwidth and parallelism is extremely larger than the device-to-host bandwidth and can be leveraged by near-data processing in a full manner. So with near-data processing, we can increase the performance by reducing the data transfer, by pushing down the queries, and by leveraging the device properties more efficiently. But how is such NDP query in practice? How does it look like? So let's look at a classical stack. We have an application which defines its application format. Below, we have a database defining the field format, the record format in its execution engine. And we have also the storage engine included in the database defining the data organization and page layout. Below this, we have the device with the already mentioned processing elements and storage chips, for instance, flash or NVM. So first, a traditional query. The traditional query is issued by the application to the database, for instance, to retrieve some fields of an object. Therefore, it uses the application format to define the object. Then this query is executed in the execution engine of the database and results in another call from the execution engine to the storage engine to retrieve the records necessary for the object to issue or to answer the original request. The storage engine, as it defines the data organization, does know where these records are placed on pages and issues another or several other commands against the device to retrieve them. The device is very simple and retrieves the pages back to the storage engine, which then passes, according to the page layout, the records from the page. With the extracted records, it is pushing down those to the execution engine, which then passes the records via the record format, and of course the fields via the field format, and can either interpret it or return it to the application itself. So for the NDP query, usually the NDP query is issued against the database or through the database to the device. And the result is either transferred to the database or even to the application itself. But the big problem is, how should the processing take place on device? Because the NDP query does not know where the data is placed on the device and how it should interpret it. For this purpose, it needs the formats and layouts defined by the upper layers. So all these have to be either attached to the NDP query or have to be available on the device. So the research problem is that traditional architectures define their formats and layouts as interface boundaries. Yet for near data processing queries, these information have to be also available on the device. So there is an explicit need for cross-layer data formats and layouts. So let's continue with the formal definition what a data format and data layout is within the context of a database management system. So data formats are defined as an element or a set of features for an element, for instance, attributes or data types, and defines how these are interpreted. For instance, the column or field types, for instance, a number or a string, and how these can be interpreted. Of course, these are also connected to the operations which can take place on such a field, for instance, the date. This can also be applied to table definitions, tuple formats. So every time a new data processing query needs to interpret some data, it needs a special data format parser for this specific element. On the right side, we have defined data layout. It defines the spatial or physical arrangement of elements within a given memory space or a container element. So to say, nested elements. Or examples for this are page layouts, such as the N-array page layout or the DSM for column stores, and of course, the record layout. This is necessary for near data processing queries when it has to retrieve data from a given memory space or a container. For instance, if it has to retrieve the records from a page, it has to use the layout to see where this is located within the page. To give a more practical example on this, I will continue showing you the architecture, the specific architecture from our evaluation. However, data formats and layouts differ among various database management systems. So, for our evaluation, we use the RocksDB as baseline or FTLKV, which is based on RocksDB and defines its storage architecture on the right-hand side. But first, let's have a look on the create table statement on the left-hand side. So our database object is images, which defines the image ID and the X and Y coordinates, so the pixel, as primary key, and the red, green, blue color information as a value. So if we'd like to work or process such tuples from the image table, in the MyRocks or RocksDB representation, we have sorted string tables as physical data storage organization, which can be iterated through via the SST iterator. And then we can extract one single SST file, which is subdivided into data and index. Via a SST parser, we can extract the elements which are within this SST file. So to say the data blocks and the index block. If we'd like to investigate one block more in detail, we use the block iterator to see that there are several records and some kind of meta information, the trailer. If we'd like to parse this block to retrieve the records, then we use the block parser to retrieve the records. Again, if we'd like to access one of the records, we use a record accessor and use as well a record parser to parse the subsequent information of a record. For instance, if our query needs to read the image ID and the color information red, it uses then in the last state the field layout and field format. And these are, depending on if it's an identifier and value, different. For instance, the image ID is a 32-bit big Indian unsigned integer, while the value, the red, is a 30-bit little Indian unsigned integer. So depending on how deep or how much the NDP operation should process the data, each and every parser has to be available on the device. So let's come to our experimental setup and evaluation. For the evaluation, we have a testbed, which comprises a host PC connected to the Cosmos OpenSSD via PCIe. The host PC has an Intel E6850 with clocked around 3 gigahertz and 4 gigabyte of RAM, 500 gigabyte SSD for the OS. The Cosmos OpenSSD is equipped with a Sync 7000 system on chip, so it has 2 ARM cores and an FPGA, and 1 gigabyte of RAM. Furthermore, 512 gigabyte of NAND flash is attached to this. Below, you can see an image of it. For the evaluation, we use a fictitious image processor application and run it once as baseline with RocksDB on a block device. For this purpose, we've configured the Cosmos OpenSSD device as a classical block device and mounted it into the Linux kernel. For the NDP query, we use NoFTLKV with some kind of NDP extension, which is able to push down the commands over the database down to the Cosmos board. We investigated 2 different operations. One is the point query, so the get pixel color, which retrieves for a certain image and pixel the respective color. Then for scan and aggregation, we have the get histogram function, which scans through an area of image or the images and return the frequency of the colors. For this purpose, we use a synthetic data set of images, which comprises around 100 million key value pairs. So let's first have a look at the get pixel color point query. We executed it 1,000 times each, and once with no caches and once with index caches. As you can see on the left-hand side, with no caches, the block device performs slightly better, yet it has a high variance in its response times. On the other side, on the right-hand side, you can see when we add some caches on the device, and of course on in the classical RocksDB, we improve the performance for the NDP around 33%. Furthermore, for the scan, get histogram, we executed it with different selectivities on the X bar and the execution time on the Y bar. As you can see, the performance linearly decreases with increasing selectivity. However, we are continuously around 27% better with NDP, and this is mainly because we can pipeline the accessors and parsers efficiently on the device. So accessors can work in parallel to the parsers and thereby improve the performance. Last but not least, I'd like to conclude our work. First of all, we have revealed the necessity for cross-layer data formats and transparent definitions of data organizations for near-data processing, as traditional architectures define their data formats and layouts as interface boundaries and are not practical to use for near-data processing queries. Furthermore, we gave some formal definitions for data formats and layouts in the context of database management systems, and presented a simple approach for such a format pushdown in near-data processing databases. For the evaluation, we have the fictitious image processor application executing on real hardware the customers open in SD port. For point queries, we've seen that the latency could be improved around 33% and seen a necessity for small on-device caches. While scans can continuously be improved around 27% and shown a efficient accessor and parser pipelining. If you have more questions about our work, please do not hesitate to contact us, and thank you very much.
Okay, thank you for that great presentation, Tobias. Does anybody have any questions? If so, please type into the chat box and I will redirect them to Tobias. Well, I don't see any questions currently. So Tobias, I have a question for you, which is, please unmute your microphone to answer. To get this to work, what was your biggest challenge? For example, was it hard to make sure you had, the relevant drivers? What about things like costs for the hardware? Was it difficult to get all the components to work properly? Like, were there any of those kinds of challenges?
Can you hear me?
Yes.
Can you?
Yeah, we can hear you. Go ahead. Did you hear my question?
Okay. So yes, basically the hardest challenge for us was to run those parsers and data formats which were databases running on classical CPUs, so use on the small ARM cores on our printed circuit board, which just has a lower clock frequency and is programmed in C style for ARM cores. So we have to programming style to the ARM core to get good results for this stuff. So this was a huge challenge for us.
I see. Okay. All right. Any other questions from the audience? Okay, there is a question here for Tobias, which is there a file system on the device, or do you have to get around the file system?
No, as NoFTL-KV operates on the NoFTL principle, so that there are no files, but the native abstraction of the flash channels, chips, and so on, we can directly place the data to exactly flash and use those physical page numbers to identify which pages belongs to which database object and so forth.
All right. Yeah, thanks for that. I don't see any other questions, so thanks, Tobias. And we will now move on to our second presentation, which is on selective caching. And I assume our speaker is Muhammad Jibril from Ilmenau in Germany. So we'll start his presentation next. Again, if there are any questions while the presentation is ongoing or at the end, please do type into the chat box and I'll redirect them to Muhammad at the end of the presentation. Thanks.
Hi, I'm Philipp Götze, and I will present today Selective Caching, a persistent memory approach for multidimensional index structures. This was originally a student project by Muhammad Jibril. And yeah, let's begin. So as a first motivation, we saw that mainly research was focusing on OLTP and B trees and bringing this together with persistent memory. And we thought, why don't we consider opportunities for OLAP and HTAP systems, like features like scalabilities, which we need there. And what we did was mainly focusing on analytical tasks and multidimensional data. And to get a general feeling about it, I put here again the table comparing DRAM, Optane, DC, persistent memory, and NAND. But the first columns are more important for us now. So on our system, we measured 80 nanoseconds for DRAM, so the sequential idle latency, and 275 nanoseconds for Optane. And it's bold, the two here, because we remeasured it again, and on our old, or with our older kernel and older firmware, we had a different number here, but now it is at 275. But what we can see here, it's like 3 or 4 times slower or takes more time than DRAM. The same is also for loaded random latency, and write latency is even harder to measure because you don't know if it is really written or only arrived at the buffer. But what we see here is, or what we think, is that PMEM is just filling the gap between DRAM and SSD and cannot replace either. Maybe more SSD, but definitely not DRAM. So we thought about how can we counter PMEM deficiencies here in a multi-dimensional setting. And first of all, we want to dig into more of the characteristic of PMEM. Maybe some of you know this already. Definitely it is persistent, as the name suggests, and it is byte addressable. So actually it's 64 byte cache line granularity. And internally it's written one line below. There's a write combining buffer, even summarizing or combining writes to 256 bytes, so to 4 cache lines. But in general, the latency, as we saw, is close to DRAM, but we have a read-write asymmetry. And the density is higher than in DRAM, which makes it more scalable and maybe also cheaper because we can fit more into one machine and don't need multiple machines. Sometimes they say it's more energy efficient. I haven't confirmed this yet, but we can trust in it. But I also heard that the controllers are more complex and maybe take more energy than DRAM. But our task now is, or question is, how can we exploit these properties? And what we have done so far is that we utilize persistence, byte addressability, and wanted to get the latency even closer to DRAM. For this, we use the Intel Persistent Memory Development Kit, PMDK, which is a de facto standard for persistent memory programming. So this is the hardware. On the software part, we use the ELF data structure, which is a multidimensional index data structure, which can also serve as a store and not only an index. And it's similar to a trie or prefix tree, however you want to name it. And here you can see, for example, if we have a table in A, with multiple columns and multiple tuples or rows. And this table is then built in B to an ELF tree, where each dimension or column is in one level, or is on the same level. And so it's very similar to the prefix tree. And so if we have 4 dimensions, we also have 4 levels. And so we are also, if we want to create the row again, so you have to traverse from the top till the bottom. So it's not like in a B+ tree where the data is at the bottom, but it is reconstructed by traversing. But the original designed ELF tree is for in-memory, and this is really optimized for it. What we can also see in C, in picture C, that was linearized into an ELF array, which is proven to be much faster in memory. And so we thought this is a natural candidate for PMEM, and we should investigate this further. So the first step, what we did now was, before caching, we wanted to persist the ELF, so make this persistent. And for this, we used PMDK features to provide full persistence and nearly, or actually no recovery at all, because everything is persistent, and we don't have to change anything later on. Yeah, if you're familiar with this PMDK stuff, then you know that you actually put stuff in a pool, which is a memory mapped file within this persistent memory. And then you have a root pointer or root as an anchor point from which you can reach all other data structures. And here we laid everything as it was an in-memory, yeah, but only had to make some modifications to make this persistent. Yeah. But as expected, or we expected, of course, a performance degeneration. So we thought, what could we do? We know DRAM is much faster. So our first idea was, why don't we have a hybrid version? We have a persistent and a DRAM version. So now put this together. So we initially built it first in PMEM. Then we copy it to DRAM on the first start and also on restarts. And then all our queries go on this DRAM stuff, which makes recovery much faster because this copy process from PMEM to DRAM is really much faster than rebuilding the complete tree in DRAM. Yeah. Okay, so this was our first idea, but then we thought, okay, what if we don't have enough DRAM or we don't want to spend so much DRAM for it because we have double the cost with this hybrid version. And then we looked at the literature. What was already done was, for example, the FP tree, which used a feature called selective persistence, where the inner nodes of a B+ tree are placed in DRAM because they can easily be reconstructed from the data in the leaf nodes, which are actually then on persistent memory. Yeah, but this is not directly applicable for us, as we have also data in the upper levels, or mandatory data. Yeah, that's why we thought, okay, let's do something similar. And we called it selective caching, which is or comes in two flavors, in the static caching and the dynamic caching. In the static caching part, we cache a fixed part of our tree, which could be, for example, the first X levels or dimensions. And with this, we don't have any probing. So we don't have an if or any branching because we know that it is in the cache and we can directly query it. And also we keep the CPU caches clean because the copy of the data is only there once. So not the PMEM and the DRAM, but only either DRAM or PMEM. Then the second part is the dynamic caching. Here we cache potentially every traversed node. Currently this is unlimited, but we want to put an eviction policy on it later on. And the selective caching is then the combination of these both strategies, so that we have a kind of split cache with a static part and a dynamic part. Also, we had the idea to cache based on specific traversing probabilities, but this is also something for future work. We only describe it theoretically. Yeah, then let's come to the setup for our evaluation. We wanted first, with our persistent variant, to quantify the overhead to DRAM, because we know there would be an overhead, but we didn't know how much would it be in practice. Yeah? So this was our first goal here. And our second goal was to scrutinize the potential of selective caching. So what which knobs do we have which we can turn and so on. Yeah, from the hardware, we have Xeon Gold 5215 with 6 DC PMM, so persistent memory modules, which are interleaved to one region and namespace. Also, we use NUMA CTL to avoid allocating and running, or avoid NUMA effects and allocate and run on the same socket. Yeah, on the software part, we have, of course, our ELF tree. We have 100 million rows in this case, 10 dimensions, and each dimension has an integer value between 0 and 100. And in total, we have then 4 GB for our tree. For now, we use the uniform access when querying, but we think this is already the worst case for caching. So if we had a skewed workload or something like this, we expect it to be even more efficient. Yeah. On the query types, we had on the first part the building of the tree. How much does this cost? And then for the actual queries, it's exact match, range scan, and a partial match scan. So this exact match is like an equal property on all dimensions. Range limits the range of the dimension, and partial match limits the range only of some of the dimensions. Yeah. For the metrics, we have the throughput in queries per second, QPS, and execution time in seconds. So our first was the evaluation of DRAM versus PMEM. And what we can see here is that especially the build time or yeah, the build time overhead is really small. So it's like only 50% slower than DRAM, which we think is mainly due to the right combining buffer. Yeah, and the exact match showed here the most optimization potential, because here it was 3 times slower than compared to DRAM, and the range and partial match part was 2 times slower in PMEM, which we think is mainly because of the sequential access pattern and because the CPU can prefetch and cache because of ranges here. Yeah. So this is the overhead we see here, 2 to 3 times, and now we tried to get this nearer to the DRAM part with our caching strategies. And here you can see as a baseline, the blue one is without caching, so this is a pure persistent one. The pure volatile one is not here, but is around the top here at 1.75 million QPS. So somewhere in between we want to get with our caching. And as we can see, we also get there. If we only use a normal or naive dynamic approach, which is unlimited, we can see it. So the orange one, we are initially faster, but later on, if the cache size increases, it is a bit self-defeating, and the probing is more costly than it gives us any benefits. Yeah. So if we use static instead, then we see we get a more stable performance. Even for one level already, we get a very good performance. And if we add more and more levels, we can see that we get closer and closer to the DRAM or pure DRAM performance, which is at 1.75. And yeah, especially the static 3 levels plus dynamic. So we statically cache 3 dimensions and the rest is dynamically cached. We get very fast or are very near the DRAM performance here. Yeah. In the end, it depends, of course, how many cached levels and dynamic, or the size of your dynamic cache. And this, on the other hand, depends how much DRAM you want to spend. Yeah? But you have a bit of tuning knobs, what you want to do here and how much you can achieve. And also it depends on the total cost of ownership, of course. Yeah. At the end, a short summary. So what do we contribute here? We contributed a PMEM-based multidimensional index structure, which provided us persistence, scalability, and efficiency, which is both in terms of monetary, but also in energy costs. And then our hybrid copy variant gives us DRAM performance, of course, because we query the DRAM part. And yeah, we also have a much faster restart because we only copy the tree instead of rebuilding it. And with our different caching approaches or selective caching, we showed that it is possible to tune it or to tune the tree to have a DRAM-like query performance and get very near the DRAM performance. Yeah. Just shortly for future work, of course, we want to have an eviction policy for this dynamic part. We wanted to parallelize queries, which is already possible with ELF, but we wanted to have our measurements clean. That's why we only made it single-threaded here. And also we wanted to utilize more DC PMM specific properties, so we could align it to 256 bytes and so on. Also, the comparison could be against the memory mode of this PMM DIMMs, and also we could compare it with a general buffering concept. But this is for future work, and I think now I'm at the end. Thanks for listening, and I'm open for questions.
And that was Philip, one of the co-authors presenting. I'm told that the first 3 co-authors are all present. So this seems like a good time to ask your questions. Are there any questions from the audience? Okay, so Philip, I had a question, which was, you mentioned that eviction policy would be future work. And you mentioned how, when you have static and dynamic, how would you do the combination? So intuitively, what do you think could be done? Or should be done?
Can you hear me?
Yeah.
Okay, so I think a simple strategy would be LRU typically. So I think at the current time it's just unlimited and an unordered map. But yeah, first idea would be LRU, but there's also a paper from Lucas Lersch, for example, who gives another idea with another policy. I think it's like, what was it called? QQ. So they also divide what to cache. A part is LRU and the other part is directly accessed in persistent memory. And I think this would also be a good idea to combine it with this. Yeah, but I think you need much more investigation, because there are, of course, a lot of other buffering strategies, and you also have the CPU caches. So you have to see where you have to, what makes more sense in this direction.
Okay. I have not. Yes, I just got a question from the audience. The question is, how do you expect this to scale into a lot larger structures? 4 GB usually fits into DRAM.
That's a good question. Yeah, we also thought maybe we should test this, but unfortunately also other people are working on this machine, so we could not use it all. But in my opinion, it should behave the same, because we had, so it shouldn't change between the bandwidth, at least for the single threaded, because we had no bottlenecks in this direction. Maybe it would be different if we have more concurrency in this case, but I think the actual size wouldn't make a difference. Maybe only of the absolute numbers, but the ratio, I would say, keeps the same.
All right. I don't see any other questions from the audience. So again, thank you for your presentation.
Yeah.
So our final presentation today is on a simulator for multi-tenant cloud databases. We're using a persistent memory-aware buffer pool. And for this, we will have a presentation from Taras Basiuk from University of Oklahoma. So again, please send me your questions via chat, either during or at the end of the presentation. Let's roll.
Good day, everyone. My name is Taras Basiuk. I'm a PhD student in computer science from the University of Oklahoma. And today I will present to you a paper entitled A Persistent Memory-Aware Buffer Pool Manager Simulator for Multi-Tenant Cloud Databases. Our presentation will consist of introduction and motivation, framework and algorithm for the proposed simulator. We will do a little experimental evaluation, and then we will conclude our work and propose some future research directions. Our work is done in the context of cloud database as a service applications, where cloud database providers such as Amazon or Amazon LDBS or Microsoft Azure offer their database services through the cloud to their clients, their tenants. So there exists a service level agreement between the cloud database provider and the tenant, which usually contains certain objectives as far as quality of that service. These objectives could be latency, uptime, time, and availability, and so on. In particular, we're interested in the database buffer pool managers, and our interest is related to the promise of non-volatile memory technologies, which are promised to be almost as fast as random access memory and almost as cheap as solid state drives. So here I'm providing a little table which show that we have these two columns with two examples of NVM technologies, and we see that they are pretty fast both for reads and for writes, and they're pretty cheap as far as price per gigabyte. However, the addition of NVM technologies to the classical buffer pool managers poses a challenge because previously when we only work with SSD and RAM storage tier layers, we only have two ways to migrate the data. We migrate the data from SSD to DRAM and from DRAM back to SSD. However, with the addition of third layer of storage tier, we place it in the middle of the previous two tiers. We end up having 4 more different data migration passes for our data. And that means that the existing design of buffer pool managers has to be extended to support that. Today, however, such an extension poses certain challenges. First of all, we don't have a very clear picture of components constituting a buffer pool manager, which works for a multi-tenant environment and which is aware of persistent memory, which is other word for non-volatile memory. Also, we have a challenge that not all researchers have a very good access to NVM hardware to experiment on. And we have a problem of high development price of modifying existing open source databases, such as PostgreSQL, for example, in order to test new components using them. So a proposed solution to tackle the above challenges is the algorithm and the framework, which we named CPBP-SIM for Cloud Persistent Memory Aware Buffer Pool Simulator. Let's take a look at our proposed framework and its components. So first of all, the input into our framework and into the algorithm which makes this framework work is the page access request sequence. So we have timestamp data which has a page ID requested by the tenant ID, and we have a certain access type which our buffer pool simulator needs to service. The second component we have a storage of page metadata, which stores the current page location and whether the page was updated or not. In other words, whether it is dirty or clean. Now, next component number 3, we have a data admission policy, which component which we say that belongs to the realm of storage tier components, and this component decides whether the page should be admitted from its current storage tier to some other storage tier or not, per certain criteria. So we propose interface for such a component, which other than initialization records access, timestamp access to certain page ID. And then the second function it implements, it basically tells us whether this page ID should be admitted to some other storage tier or not. Now, when we decide that the page should be admitted somewhere else, we have a data migration policy component which says, upon admission or eviction of page from its current storage tier, where should that page go? Yes, so this interface of such component will implement 2 functions, destination on admission and destination on eviction of the page from its current storage tier. Next, we have, let's say, data admission policy told us that our page needs to go to the, let's say, RAM tier. But RAM tier at the moment ran out of free space, so we invoke data eviction policy to find a page to evoke from that storage tier, right? So we have this data eviction policy. Again, it records accesses to different pages to be able to make an intelligent decision in the future. And then it has eviction policy, which basically says, okay, among the pages currently stored in our storage tier, which one should be evicted next. So the next component, we have parameters, storage tier component, storage tier parameters, which basically stores the amount of unused space in that storage tier, and it also records SLO costs. SLO is a service level objective, which is a part of SLA. So we can have different objectives related to how much latency, energy, or endurance the servicing of page access requests we should, what kind of cost we should incur. And as we incur those costs are recording in SLA violation penalty function, right? So we record SLO cost of page access for SLA of tenant making the request. All right, next, we also have a metrics monitoring component whose goal is to record metrics and maybe to record metrics which are unrelated to tenant SLA, and we use them to extract more insight into the operation of our algorithm, of our simulator, and operation of our components, to basically try to figure out, well, why the performance is such as it is. As we record SLO costs against our SLA violation penalty function, eventually we will actually evaluate that penalty, and we will basically tell, okay, from this particular time, how much penalty we actually incurred and how much penalty the cloud database provider will have to pay to the tenant ID as a result of operation during a certain period of time. So we have these examples for 4 different tenants, how much money we will end up paying to them as a penalty. All right, so now we can look at the algorithm for the simulator itself. So for the component in the middle of our framework. So here it's pretty big algorithm. So we provide as an input, we describe all the components of the framework and the input data, which we went into previously. So now then we start the simulation. So for each of n requests, we go ahead and now next, we figure out the current storage tier of the requested page. We check with the data admission policy whether it should be admitted to some other storage tier with CPU access. And if it should, we ask data migration policy to figure out where should it be admitted. Now, if the destination storage tier of that page does not have enough free space, we check with data eviction policy of that storage tier to figure out the victim page. And then we ask data migration policy to tell us where that victim page should go. Once we establish a chain of required page migrations, we calculate the total SLO cost, so let's say total latency of said chain, incurred on behalf of the tenant, and update the page metadata. So we update where the page is located and whether it's now dirty or not. And then we also record the requested page access with data admission and data eviction policy. We record the SLO for the tenant, and we record other metrics. And once we done services all the page requests, we calculate the penalties incurred on behalf of every tenant by the cloud provider. So now let's see. So the goal of our experiment was to show the robustness of our simulator framework. So we configured it with 3 storage tiers: SSD, NVM, and RAM. So we gave RAM the least space, NVM medium amount of space, and SSD the most space available. So we configured the system to have 3 different kinds of tenants, so 9 tenants at all. So we have bronze, silver, and gold, signifying gold is like a higher subscription tier, bronze is a lower subscription tier, and then we describe our tenant SLA violation penalty functions. So they are tied to SLO. We evaluate them every 10 seconds for the average latency, and if the average latency is above certain cutoff, we incur a certain penalty on behalf of that tenant. So then we run a set of experiments. So for the baseline, we use eager data migration, data admission policy. So every time a page is requested on SSD or NVM tier, we admit it to a different tier. We use very simple first in, first out data eviction policy for NVM and RAM tiers. And then our data migration tier, there's a 50-50 chance we migrate the page to NVM or on where it's admitted to SSD. and the same chains we migrated to NVM or SSD when it's evicted to RAM. So once we establish the baseline, we run LRU experiment where we use LRU data eviction policy, so a more advanced policy for RAM. And you see that the difference between the accrued penalties is not very big. That's because the RAM has only accounts for about 10% of our fast memory, so that doesn't help much. However, when we use LRU policy for both RAM and NVM, you can see that our average total penalty goes down. However, our runtime of our simulator also goes up. Then we use a 2Q data admission policy, which basically doesn't admit the page to next tier right away. It has to see the page once before it admits it somewhere else. And we see that actually using this penalty makes things worse. And we speculate that's because it slows things down for the gold tenants access to the fast RAM space. However, then when we try to use heterogeneous data migration policies, so for the bronze tenants, we promote things to the RAM layer and NVM layer slower, versus for gold tenants, we promote things to RAM faster, and we demote things from RAM to SSD slower. So in such a case, you can see that the penalty for the gold tenants go down significantly. It goes up for the other tenants also significantly, but because the penalty for gold tenants is so high, the overall total penalty goes down. All right, so to conclude, we propose a comprehensive overview of components constituting our multi-tenant persistent memory-aware buffer pool manager. We proposed the simulator algorithm, and we demonstrated the utility of framework and algorithm for rapid prototyping of novel buffer pool manager components. For the future work, we plan to leverage biodiversibility property of the storage tiers. So when data migrates from RAM to NVM, we don't have to copy the entire page. We only can copy some portion of data. Then we plan to evaluate the accuracy of the simulator, and we plan to obtain input paid access request sequence equivalent to the industry standard query benchmark and using them for the simulation. Now I thank you for your time, and that's it.
All right, thank you, Taras, for that presentation. We are now open for questions. If you have any questions, please type in the chat box and I'll direct them to the speaker. So we have a question for Taras, which is, does the simulator assume that the DRAM cache is a subset of the NVM cache?
No, we actually treat them separately. So we treat them as two separate storage tiers. So we have a DRAM tier and we have NVM tier. And we track the available space, and we attach different data eviction and data admission policies to different tiers. And also for different tenants, we have different data migration policies which decide whether more of tenant data will reside on RAM or NVM tier. So basically the idea is for the tenants who have very small but often accessed working set size, we will try to keep more of their data in RAM. However, if the tenant has not as hot data, so warm data, we will allocate more of the NVM space for them. So.
All right.
Yes, yes, and we also, in this scenario, we consider a scenario when NVM is a CPU accessible device. So we're not talking about NVMe devices, not the disk replacements, but yeah, this work was done in the for the NVM devices accessible by CPU.
Okay, so just to clarify, is this a question you're answering with respect to can a query directly visit NVM without visiting DRAM?
Yes.
Okay, yeah. Just wanted to double check. I have one question for you, which is, so, if I were to go on, say, AWS, and I'm picking out various resource instances, right? There are things like vCPUs, and it's, for me, at least, it's never clear what a vCPU means, despite what Amazon says, which is, that, it's a thread and so on. So in your simulator, do you care about this? Do you capture it in some way?
The simulator has, it does not enforce what kind of service level objective you will be using, right? It does not make you use virtual CPUs or, or whatever virtual resources. The developer of the novel components have a freedom to choose what kind of SLOs they will use. And the assumption there that, yes, perhaps some of the SLOs the researcher will be using is not something you can expose to the tenant very easily, because there is this problem in cloud environment when objectives of your service, such as, I don't know, buffer pool hit rates or amount of buffer pool memory actually used by the tenant data, is not a data which you can expose to the end user very easily, because end user very often does not actually know, well, how much of the cache cache memory space do I need, or what sort of buffer pool hit rate do I need. So the simulator assumes that perhaps some of the SLOs you can configure it with will be like internal objectives, not actually exposed to the end customer.
Right, thank you. That concludes the last of our research presentations. Thank you all for attending and for your questions. And I'd like to give a special thank you to Brian Ricks for supporting, this whole process and making it easy for us, the workshop organizers, to conduct this. And hopefully it was fairly straightforward for all the attendees. We are going to be in the SMDB room in half an hour, so 1 p.m. Eastern Daylight or 12 p.m. Central Daylight Time for the next keynote, which is a joint keynote between HeartDB Active and SMDB. Thank you again, and we'll see you in about half an hour.